What if your soulmate was not chosen by fate, but by an algorithm? Well, that is exactly the question I'm going to talk about today. And a spoiler alert, yes, there exists an algorithm that can find a stable matching between a group of n men and n women. This is the Gale-Shapley algorithm. Back in the 60s, David Gale, a computer scientist, and Shapley, an economist, worked on this problem. And in 2012, Shapley, together with Ross, was awarded the Nobel Prize for this work in economics. Unfortunately, by that time, Gale was not alive. In this video, we are going to talk about the simple version of this question and this algorithm, where we have two groups, each with n people, and each person has a preference list ranking the people in the other group. And the goal is to find not just matching, not just perfect matching, but a stable matching. Before we get into the algorithm, let's quickly talk about these definitions. First, matching. A set of pairs connecting people in group 1 to group 2. No one is allowed to have more than one partner, but it is okay if someone is single. 2. Perfect matching. It is the same as matching, but this time singles are not allowed. So we have exactly n pair of men and women such that each person is exactly matched with someone else in the other group. And third, stable matching, where we have a perfect matching with no unstable pair. But wait, what does an unstable pair mean? Every time I teach about stable matching, some students think unstable pair is about an existing couple who are not happy or who don't like each other. But it is not correct. Unstable pair is not about an existing pair. It is about a potential couple. Actually, it means we are talking about two people who like each other more than their current partner. And sooner or later, they are going to break up with their current partner and get matched with the other person. So, unstable pair is something that we don't want in our matching. Stable matching doesn't mean that everyone is happy. Actually, it means that no pair has incentive of leaving their current partner. Before diving into the algorithm, we are going to see two examples and we are going to ask two questions. Does a stable matching always exist? And if yes, is it unique or it is possible that for a given input, we have more than one stable matching? Let's take a look at these examples. In this example, we have two women and two men. Now, let's take a look at their preference list. Red prefers blue over yellow, and green has the same opinion and the same rank list. The situation with men is also the same. They have the same rank list. They both prefer red over green. So the question is there any stable matching in this example? The answer is yes. If we match red with blue and green with yellow, we claim that it is a stable match. The reason is that in this example, red and blue are happy. I know green and yellow are not happy, but they don't have any option to be with someone better. So the cases are stable. Now let's take a look at the second example. Again, we have two women and two men. Now let's take a look at their preference list. Red prefers blue over yellow, but green prefers yellow over blue. Blue prefers green over red, but yellow prefers red over green. So the same question, is there any stable matching in this example? The answer is yes again. If we say red and blue are together and green and yellow are together, it is a perfect match. In this case, red and green are happy. If we say green and blue are together and red and yellow are together, again it is a stable match. The reason is that blue and yellow are happy. Note that if everyone in one side is happy, then it is all good. We don't really care about the other ones because they don't have any option. Now let's talk about the idea behind the Gale-Shapley algorithm. Gale and Shapley said we have two groups, men and women. So let's say one group is proposal giver and one group is proposal receiver. Until the end of the algorithm, we will have some matches that are not final, but at the end of the algorithm, we are going to return a match that we claim is a stable match. So during the algorithm, to this non-final match, we can call them something like engagement phase. So in each iteration, we find someone from the proposal giver group. That someone must be single. Also, they shouldn't have proposed to everyone in the other group. So there must be someone who they hasn't proposed to yet. So they are going to take a look at their rank list and find the top person who they haven't proposed yet. And they are going to propose to that person. Not this person. If this person is single, they are going to accept the proposal immediately, even if they don't like this person. If they are matched with someone else, they are going to see if they prefer their current partner or this new person. If they prefer their current partner, they are going to reject this person and continue their relationship with the current partner. But if they like this new person better, they are going to break up and start a new match with this new person. We are continuing these iterations until there is no single person, and if there is a single person, they must have proposed to everyone. But is it possible that we have a single person who has proposed to everyone? I can say no. The reason is that for every one person in the proposal giver group, there must be one single person in the proposal receiver group, because we have n men and n women. So if this person is single, there must be a single in the other group. But it means that at some point, this person must have proposed to this person. But why are they single now? If they were single at that moment, they must have accepted. It is what the algorithm says. But maybe they were in another match. But if they were in another match, why are they single now? Because the only reason they are not in a relationship now is that they found someone better, so they switched. Because in the proposal receiver group, there is no possible case that someone who is in a match just decides to get single. And the only reason they break up is to upgrade. So once they are in a relationship, they are going to continue being in a relationship. It is something that we can say for proposal receiver group. It is not correct about proposal giver group because they can get matched, but the other person can break up. This person is single again and they propose to someone else, and they can be in relationship single, over and over. Okay, so the only case that this iteration or this while loop will stop is because there is no one who is single anymore. And now we have a perfect matching, and we want to claim that it is a stable matching. First, let's take a look at the problem line by line, and then we'll talk about why the matching is stable. Okay, now let's go through propose and reject Gale-Shapley algorithm line by line. In this algorithm, or in this version, we assume that men are proposal giver side and women are proposal receiver. So we start with assuming that all men and women are free at the beginning. And then we find a man who is free and hasn't proposed to every woman. We choose such a man, M, and we say that, okay, now propose to the highest ranked woman in your list. Let's call them W. Now we have three cases for W. If W is free, W is going to accept, and M and W are going to become a match. Else, if W is already matched to someone else, let's say M prime, they are going to see if they prefer M over M prime or not. If they prefer M, who is the new proposal giver to W, over M prime, they are going to break up with M prime, and M and W become matched. Note that now M prime becomes unmatched. But if W prefers their current partner, M prime, to M, they are going to reject M, and M remains free. We are going to continue this while loop until there is no free man who hasn't proposed to everyone. Okay, now it's time to prove Gale-Shapley actually returns a stable matching. We want to use proof by contradiction. I hope that everyone is familiar with proof by contradiction, but if you are not familiar, just leave me a comment and I will explain it in another video. Okay, proof by contradiction in this example says that let's assume what we want to claim is not correct. So it is not a stable matching. If it is not a stable matching, so there must exist a pair which is unstable pair. Do you remember the definition of unstable pair? Unstable pair are two people who are not in relationship, who are not matched with each other, but they prefer each other over their current partner. So if we have unstable pair, let's see the situation. So let's think about this person in the proposal giver side. If they are in the proposal giver side, they must have a rank list and they must prefer this new person who is not in a match with them over their current partner. So it means that they were higher ranked. Why they didn't propose to this person? They must have proposed. If they have proposed, why aren't they together? So it means that the woman in the proposal receiver side preferred someone else at some point. So either they rejected because they were with someone better, or at some point break up because they found someone better. So why aren't they happy now with their current partner? Actually, it is a contradiction because there is no way that this person, the proposal receiver side, preferred this proposal giver side over their current partner, but they rejected them at some point. Because we know that the proposal receiver side always upgrade. So if they find someone better, they switch. If they find someone worse, they don't switch. It is a proof by contradiction showing that Gale-Shapley algorithm actually returns stable matching. Now, let's talk about time efficiency or time complexity of this algorithm. See, we could design a very easier algorithm by saying that, okay, just try all the possible matching and then test which one is stable and which one is not. But in order to find all matchings, we need n factorial different matchings, which means that it is in order of n factorial. If you don't know about big O notation, I'm going to talk about that in the other videos. So it is O of n factorial. N factorial is in fact an exponential algorithm. O of n factorial is not efficient. But in this algorithm, we had a while loop and each person in the proposal giver side, which are n in total, can propose to at most n people in the proposal receiver side. So in total, the maximum number of proposals that we could have is n square. So Gale-Shapley's time complexity is O of n square and is polynomial, so it is an efficient algorithm, comparing the exhaustive search of finding all the pairs and testing if they are stable or not. Okay, it was stable matching Gale-Shapley algorithm when we have n men and n women. It has lots of applications in college student matching, intern matching to companies, resident matching to hospitals. But in those examples, it is possible that the number of each group is not exactly the same as the number of the other group, which means that the number of residents most of the time is more than the number of hospitals, or the number of interns is more than the number of positions for interns. We are going to talk about these cases in other videos as well. Thank you so much for watching this video. See you in the next video.